applications of derivatives, rate of change of quantities, monotonic increasing and decreasing functions, and maxima and minima of functions of one variable. From G Main Unit 7. Essential for Class 11, 12, and G. Part A. Rate of change of quantities. The average rate of change is delta y over delta x, which equals f of x plus h minus f of x over h. Geometrically, it's the slope of the secant line between 2 points. The instantaneous rate of change is the limit as h approaches 0, giving us dy by dx, the derivative. Geometrically, it's the slope of the tangent line at that point. Watch on the graph, the orange secant lines get closer and closer to the green tangent as the second point slides toward the first. That limiting slope is the instantaneous rate of change. Visual demonstration. For a circle with area A equals pi r squared, the rate of change of area with respect to radius is da by dr equals to pi r. Watch the circle expand. Each ring of growth adds more area than the previous one because the circumference is larger. The bar chart shows, at radius 1, the rate is 2 pi. At radius 2, it doubles to 4 pi. At radius 5, it's 10 pi. The rate of area growth increases linearly with radius. This is a beautiful connection between geometry and calculus. Example 1. Air is pumped into a spherical balloon at 12 cubic centimeters per second. Find the rate at which the radius increases when the radius is 3 centimeters. Volume of a sphere, V equals 4/3 pi r cubed. Given dV by dt equals 12. By chain rule, dV by dt equals 4 pi r squared times dr by dt. Substituting, 12 equals 4 pi times 9 times dr by dt. That gives 12 equals 36 pi times dr by dt. Therefore dr by dt equals 1 over 3 pi, approximately 0.106 centimeters per second. The radius increases slowly even though volume increases fast, because more volume is needed for each unit of radius growth. Example 2, the classic sliding ladder problem. A 5-meter ladder leans against a wall. The base slides away at 2 meters per second. Find how fast the top slides down when the base is 3 meters from the wall. By Pythagoras, x squared plus y squared equals 25. When x equals 3, y equals 4. Differentiate implicitly with respect to time, 2x times dx by dt plus 2y times dy by dt equals 0. Substitute, 2 times 3 times 2 plus 2 times 4 times dy by dt equals 0. 12 plus 8 times dy by dt equals 0. Therefore dy by dt equals negative 3 over 2 meters per second. The negative sign means the top is sliding down. As the base moves right, the top must fall. Part B. Monotonic functions. A function is monotonic on an interval if it goes consistently in one direction, either always increasing or always decreasing. Increasing means, if x1 is less than x2, then f of x1 is less than or equal to f of x2. The derivative is non-negative. Decreasing means, if x1 is less than x2, then f of x1 is greater than or equal to f of x2. The derivative is non-positive. The key insight, the sign of the first derivative completely determines whether a function is increasing or decreasing. Visual comparison. On the left, an increasing function, the curve always goes uphill, the derivative is always positive. Dot tracing upward. On the right, a decreasing function, the curve goes downhill, derivative always negative. But most functions are not monotonic everywhere. The bottom graph shows a typical function, green segments where it increases, f prime positive, red segments where it decreases, f prime negative. The function changes behavior at critical points where f prime equals 0. Important distinction, strictly versus non-strictly monotonic. Strictly increasing means f of x1 is strictly less than f of x2 whenever x1 is less than x2. The derivative is strictly positive, the function always goes up, never flat. Non-strictly increasing allows flat portions, f of x1 less than or equal to f of x2. The derivative can be 0 at isolated points. On the graphs, left shows a strictly increasing function with no flat parts. Right shows a staircase-like function that is non-strictly increasing, it has flat segments but never decreases. In G, most problems test strictly increasing or decreasing functions. Example. Find intervals where f of x equals 2x cubed minus 9x squared plus 12x minus 5 is increasing or decreasing. Step 1. Find f prime. F prime of x equals 6x squared minus 18x plus 12, which factors as 6 times x minus 1 times x minus 2. Step 2. Set f prime equal to 0, x equals 1 or x equals 2. These divide the number line into 3 intervals. Step 3. Test the sign in each interval. For x less than 1, both factors negative, product positive. f prime positive. Between 1 and 2, x minus 1 positive, but x minus 2 negative. F prime negative. For x greater than 2, both factors positive. F prime positive. Conclusion, f is increasing on negative infinity to 1 and on to infinity. F is decreasing on the interval 1 to 2. The graph confirms this. Part C, Maxima and Minima. A critical point is where f prime equals 0 or doesn't exist. A local maximum is where the function value is greater than or equal to all nearby values, the hilltop. A local minimum is where it's less than or equal, the valley bottom. On the graph, watch the dot trace the curve. At each local max and local min, the tangent is perfectly horizontal, meaning f prime of x equals 0. But remember, f prime equals 0 is necessary but not sufficient. We need additional tests to confirm if a critical point is actually a maximum, minimum, or neither. Test 1, the first derivative test. Step 1, set f prime equal to 0 to find critical points. Step 2, check the sign of f prime on either side of each critical point. For a local maximum, f prime changes from positive to negative, the function goes uphill then downhill, like a hilltop. For a local minimum, f prime changes from negative to positive, downhill then uphill, like a valley. If the sign does not change, positive to positive, or negative to negative, then it's neither a max nor min, it's just an inflection point. The three mini-shapes illustrate each case perfectly. Test 2, the second derivative test, often faster and simpler. At a critical point C where f prime is 0, if f double prime of C is negative, curve is concave down, it's a local maximum. Think upside down cup, hilltop. If f double prime of C is positive, curve is concave UP, it's a local minimum. Think cup shape, valley. If f double prime is 0, the test fails. Use the first derivative test instead. Why does this work? If f double prime is negative, the slope is decreasing. So slope goes from positive to 0 to negative, exactly the pattern for a maximum. The big advantage, you only compute one number, f double prime at C, no interval testing needed. Example 3. Find the local maxima and minima of f of x equals 2x cubed minus 9x squared plus 12x minus 5. We already found f prime equals 6 times x minus 1 times x minus 2, giving critical points x equals 1 and x equals 2. Now apply the second derivative test. F double prime of x equals 12x minus 18. At x equals 1, f double prime equals negative 6, which is negative. So x equals 1 is a local maximum, with value f of 1 equals 0. At x equals 2, f double prime equals 6, which is positive. So x equals 2 is a local minimum, with value f of 2 equals negative 1. The graph confirms a peak at x equals 1 and a valley at x equals 2. Example 4, a classic optimization problem. Find two positive numbers whose sum is 24 and whose product is maximum. Let x plus y equals 24. So y equals 24 minus x, product p equals x times 24 minus x, which is 24x minus x squared. Differentiate dp by dx equals 24 minus 2x. Set it to 0, x equals 12. Second derivative, d squared p by dx squared equals negative 2, which is negative, confirming it's a maximum. So both numbers are 12, and the maximum product is 144. The parabola shows p peaks exactly at x equals 12. This proves, among all pairs summing to 24, equal halves give the largest product, a powerful general principle. Absolute or global maxima and minima on a closed interval. The method is straightforward. First, find all critical points inside the interval. Second, evaluate f at each critical point. Third, and this is crucial, evaluate f at both endpoints A and B. Fourth, the largest value is the absolute maximum. Fifth, the smallest value is the absolute minimum. Important warning, endpoints can be absolute extrema. On the graph, the local max is inside the interval, but the absolute minimum is actually at the left endpoint. Never forget to check endpoints in closed interval problems. Key exam tips. First, in rate of change problems, always set up the chain rule connecting the variables. Second, if f prime is positive everywhere on an interval, the function is strictly increasing there. Third, f prime equals 0 is necessary but not sufficient for extrema. Fourth, the second derivative test is usually faster, just plug in. Fifth, if f double prime is also 0, fall back to the first test. Sixth, for optimization, express everything in one variable first. Seventh, on a closed interval, always check endpoint values, they might give the absolute max or min. Eighth, equal values give maximum product, this connects beautifully with the MGM inequality. If you found this helpful, like and subscribe for more JEE and board exam solutions at MAGPIEHUB.